right, we're going to use Taylor or Maclaurin series to approximate a function. And then we're going to use figure out the error of a polynomial approximation using Lagrange error bound rules. Okay, so what we're going to do is expand our polynomial to the fourth degree, and we're going to center at x equals 0 and approximate the function f of 0.2 for the function e to the x. All right, we already know that f of x is equal to e to the x, which will expand to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus dot dot dot. Okay, so if I want to use a polynomial, a fourth degree polynomial to evaluate this function, I'm just going to say that f of 0.2 is not equal, because it's an estimation, is about equal to 1 plus 0.2 plus 0.2 squared over 2 factorial plus 0.2 cubed over 3 factorial plus 0.2 to the fourth over 4 factorial. And I'm not going to put the dot 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 because I'm only using those 5 terms to evaluate. Okay, so I get f of 0.2 is about equal to 1.221. Okay, if like you don't have this polynomial memorized, remember you can always take your f of x is equal to e to the x, take the first derivative, e to the x, the second derivative is e to the x, and then you're going to take, evaluate the function at each one of the c values. So f of 0 is equal to 1. F prime of 0 is equal to 1, f double prime of 0 is equal to 1, and then plug it into the power series expansion, which would be f of x, or f of c, plus f prime of c times x, plus f double prime of c times x squared over 2 factorial, plus it continues. Okay, so what we are going to do now, just for fun, I typed f of 0.2 in the calculator, which was e to the 0.2, and the actual value is 1.221. So close. Okay. All right, so the error is associated with, there's an error associated with any approximation. Okay, so anytime we approximate a value, of course, we're going to be off by a little bit. Okay, so what we've seen that when we have the alternating series, that the error is the value of the absolute value of the first unused term. That's the most that we're going to be off by. Okay, but what happened, or yeah, but what happens if the series does not alternate? Then I have this other rule, or this other strategy called Lagrange. Okay, and we're gonna pause because my dog is being crazy. Okay, so the error of a polynomial to the nth degree centered around x equals c is equal to the polynomial's value minus the actual value, okay? Or the other way, you can do actual minus polynomial and take the absolute value, okay? And that value, the error is going to be less than the first unused derivative, So the next term, the derivative of the next term, not the derivative of the next term, it's the derivative of the next term. Anyway, the next derivative, at some value of z that is going to be the highest value that we're going to estimate, and then over n plus 1 factorial. So all of this is like the same, times x minus c to the n plus 1. So this is really just the next term, like the highest value of what we think the next term is going to be. Okay, so what we know is the next term. The next term. So this value, f of n plus 1 of z, I'm going to explain that to you in an example. Okay, so the next thing we need to do is know that this value of z, we don't really care where we're evaluating the z value. We just are estimating the highest value of the derivative that we think it's going to be. Okay, so here's the deal. I'm going to use Lagrange error to prove that the actual minus the polynomial, so the value of f at 0.2 minus the estimation at 0.2 is less than 1 over 1,000 from our e to the x example. Okay, so what we used is to the 4th degree term. So our next term would be x to the 5th over 5 factorial. Okay, and then from my Lagrange error, what I'm going to do is, we know that the error is going to be, less than or equal to f of n plus 1 of z over n plus 1 factorial times x minus c to the n plus 1. Okay, x of naught. X of naught is the value that we evaluated our function at. We evaluated at 0.2. Okay, c, our function was centered around 0. And n, the last used term was 4. So our first unused term would be 5. Okay, so what we're going to do is take our error is equal to f of n plus 1 times x sub naught minus c to the n plus 1 over n plus 1 factorial. Okay, of z. All right, here's the deal. This value is weird. Again, it's just the maximum value that we think is going to be the derivative of f, the 5th derivative of f. So this is going to be the 5th derivative of f evaluated at something times 0.2 minus 0 to the 5, because this is the first unused term, okay, over 5 factorial. Again, now we need a value for this f to the 5th of z. So I am just going to replace it with the max value, okay? So the maximum value, and then I have a little note over here. Okay, so what is the max value? The max value is the maximum value of the 5th derivative of e to the x on the interval 0 to 0.2. So from my c value, that's basically my c value, to the value I evaluated at. So the 5th derivative of e to the x is e to the x. So when would I have the greatest output on the interval 0 to 0.2? Well, it's when I plug in a higher value for x. So the max value would be e to the 0.2, okay? But because, like, I'm trying to do this without a calculator, I'm just going to say that e to the 1, like 0.2 is definitely under e to the 1, okay? So this is about equal to 2.7, which is, again, less than 3. So I'm going to plug in 3 for my max value, and this is a very conservative. Like, we way overvalued our max value. Okay, so I'm going to plug in a 3 right here for the max value times 0.2 to the 5th, which is just 1/5 to the 5 over 5 factorial. Okay, so I'm going to multiply that out. We get 3 over 5 factorial is 120. And then 5 to the 5 is 3,125. And what I know is that we just want to show that our error is less than 1 over 1,000. So we know that this error, 3 over 120 times 3,125 is definitely less than 1 over 1,000. Okay, so that's it. That's all we got to do. Okay, so even with a very conservative number or overestimate for the max, okay, of f to the f, the fifth derivative of f evaluated at z, it yields, we still yield an error less than 1 over 1,000. Okay? All right, next. So we're going to let f be a function given by sine of 5x plus pi over 3, and let p of x be a third degree polynomial, all right, of f about 0, so centered at 0. And we're going to find p of x, then use the Lagrange error bound to show that the actual minus the estimate, or in other words, the error, is less than 1 over 1,200. All right, so we better expand this. I am just going to expand this like f of x is equal to the sine of 5x plus pi over 3. So, because this seems easier to me. So the derivative of sine is cosine of 5x plus pi over 3 times the derivative of the inside, which is 5. So f double prime of x would be negative sine times of 5x plus pi over 3. And then we need to multiply the 5 with the inside 5, which gives us 25. Okay. And then f triple prime of x would give me negative cosine of 5x plus pi over 3. And 25 times 5 would give me 125. All right, so f of, we are centering around 0. So f of 0 is sine of pi over 3. And if you don't remember your trig, let's draw ourselves a triangle. Pi over 3, we have root 3 over 2 as the y, 1/2 as the x, and 1 as the radius. So sine of pi over 3 is the y, we get root 3 over 2. F prime of 0 is 5 times the sine of pi over 3, which would give, the cosine, which is 5 times 1/2, so 5 over 2. F double prime of 0 is negative 25 times the sine of pi over 3. So negative 25 root 3 over 2, and f triple prime of 0 is negative 125 times the cosine of pi over 3. So we're going to multiply 1/2 by negative 125, so negative 125 over 2. All right, we can write our polynomial. So p of x is equal to, it has to be to the third degree, so that means I need to take the third derivative. First derivative at 0 is root 3 over 2 plus first derivative at 0 is 5 over 2 times x plus, actually it's minus 25 root 3 over 2 times x squared over 2 factorial, okay? And then another minus 125 x to the third over 2 from the denominator of f triple prime times 3 factorial. All right, so that is our polynomial, third degree polynomial here. That's this part. Okay. And now we're going to show the Lagrange error bound is less than 1 over 1200. Okay, so the max error is equal to the maximum, the derivative of the maximum value of the first unused derivative. There we go. So this would be f, the fourth derivative of f evaluated at z. Okay, we'll get there in a second. Over 4 factorial times x sub naught is, what we're evaluating is 1 over 15, so that would be x sub naught. Okay, and then minus 0 because that's x sub naught and c, all raised to the 4th power. So this is our first unused term. Okay, I'll just write it over here. It's f, the fourth derivative of f evaluated at z times x sub naught minus c to the 4th power over 4 factorial. Okay, so the max value of the fourth derivative of, I'll just write this out. The max of the fourth derivative of f evaluated at z on the interval 0 to 1 over 15, so that's your c value and your x sub naught value. So like, what is the max value of the fourth derivative of f? So let's go ahead and take the fourth derivative of f. So the third derivative was negative 125. So the fourth derivative of f evaluated at x would be it would be positive 625 times the sine of 5x plus pi over 3. Okay, so we know that sine oscillates, okay? Goes up and down and up and down. And this sine function has an amplitude of 625. So even if 625 doesn't happen between 0 when x is 0 to 115, or z is between 0 and 1 over 15, we know that the maximum value of the function 625 of sine of 5x plus pi over 3, that the max value is the amplitude of 625, okay, because of the amplitude. So I'm going to go ahead and substitute this in for the max value. Okay, so I get 625 is the maximum value of the fourth derivative, okay, times 1 over 15 to the 4th over 4 factorial. Okie doke. I'll do this without a calculator. So I'm going to do 625 over 15 to the 4th times 4 factorial. And I know that 15 to the 4th can be rewritten as, let's also rewrite this 4 factorial as 24. So 24 can be rewritten as 8 times 3, and then 15 to the 4th can be rewritten as 15 squared times 15 squared. Okay, so this is 225 times 8 and 225 times 3. So just doing like friendlier numbers here. Okay, so you get 625 is over 225 over 8 is 1800 times 725. Okay, which, look, I know that this value right here, 625 over 725, I can write this like times 1. So 625 over 725 is already less than 1. So I know that the fraction 625 over 1800 times 725 is less than 1800, which therefore must be less than 1 over 1200. So our error is going to be smaller than 1 over 1200. And that's that. Okay, last one. So we're going to write a third degree Taylor polynomial. So third degree Taylor polynomial about x equals 2. So that means c is equal to 2. And we're going to use it to approximate f of 2.3. If the fourth derivative of f satisfies the inequality, the fourth derivative of f of x is less than or equal to 9 for all x in the interval. Use the Lagrange error bound to find an interval on a to b such that a is less than or equal to f of 2.3, and that's less than or equal to b. Okay. So here we go. We know that x equals 2 is where we're centered. So I'm going to highlight this. We are centered at c is equal to 2. So we can write our polynomial. The polynomial at x is equal to f of x, which is f of 2, which is 6, plus f prime of 2 times x minus 2, because we are centered at 2, minus 7 times x minus 2 squared over 2 factorial, plus 8 times x minus 2 cubed over 3 factorial. All right, and then if I want to evaluate this, f of 2.3 is about equal to, and all I'm doing is plugging in 2.3 in for x, which makes this my x sub naught. Okay, so I'm doing 6 plus 4 times 2.3 minus 2 minus 7 times 2.3 minus 2 squared over 2 factorial plus 8 times 2.3 minus 2 cubed over 3 factorial. And so f of 2.3, when I evaluate using my calculator, is 6.4921. Okay, so that's about how much it's equal to. And now let's check out our error. Okay, so the error is going to be the next unused term. So it's going to reference f of, we use the third degree polynomial, so the fourth derivative at some x value of x sub naught minus c to the fourth over 4 factorial. First unused term. Okay, so we usually write this as the max value, remember, times x sub naught minus c to the fourth over 4 factorial. Okay, so the max value, the max is the highest value. We want the max value of the fourth derivative of x or of z. So I'm going to look at I'm going to look at my table first. And like first derivative, second derivative, third derivative, fourth derivative. Well, whoa, there is no information about the fourth derivative. So then I'm going to go back and read the problem, because usually they sneak in a piece of information that tells me about that I absolutely have to use for this, okay? So it says, if the fourth derivative of f satisfies the inequality, the absolute value of the fourth derivative is less than or equal to 9. Oh, look, my max value. My max value is 9, okay? So because the fourth derivative of f has to be less than or equal to 9. So I'm going to substitute in 9 for the max value. Over 4 factorial, x sub naught is 2.3 minus 2 to the fourth. Okay. So the max, I'm going to just do this in my calculator, and I got the max error would be equal to 0.00300375. Okay, so f of 2.3 has to be less than or equal to our estimation, which is 6.4921. So 6 point, I think do I need the 4 or do I not need the 4? Let me double check. Okay, so I made a mistake, and the value, the estimated value of the function is 6.921. So take out that little 4 that I accidentally put in there. So when I figure out the max value, it's going to be 6.4, 6 point, oh, there we go. Okay, so the actual value, this is the actual value, has to be less than or equal to 6.921 plus the potential error, 0.0030, or it has to be greater than my estimate, 6.921 minus the error. So there's a range of error. Okay, so I get f of 2.3 has to be less than or equal to 6.924, but greater than or equal to 6.918. So this tells me my estimate or my approximation plus the error, potential error. And this is the approximation minus the error. Okay, and that's that.